India's Mars orbiter mission, known as Mangalyaan, is one of the most remarkable achievements in the history of spaceflight. Launched on the 5th of November 2013 by the Indian Space Research Organization, it became the first Asian mission to reach Mars orbit, and it succeeded on the very first attempt. Its total cost was just $74 million, making it 9 times cheaper than NASA's MAVEN mission launched the same year. This was not luck, it was the result of brilliant trajectory design, deep knowledge of orbital mechanics, and ruthless propellant budgeting. In this video we walk through the complete astrophysical architecture, from Newton's equations of gravity, through the Hohmann transfer in the Oberth effect, to the critical Mars orbit insertion burn that made history. Everything in this mission is governed by 2 core equations. First, Newton's law of universal gravitation. Force equals G times m divided by r squared. We immediately absorb G and m into one quantity, mu, the standard gravitational parameter. For Earth, mu equals 3.986 times 10 to the 14. For the Sun, it is 1.327 times 10 to the 20. Second, the Vis-Viva equation. V squared equals mu times the quantity 2 over r minus 1 over a. This single equation gives the orbital speed at any point in any Keplerian orbit. It is the workhorse of every delta V calculation in this mission. For a circular orbit, a equals r, and Vis-Viva simplifies to V equals the square root of mu over r. Escape velocity is the square root of 2 mu over r, always 1.414 times local circular velocity. Orbital energy epsilon equals versus squared over 2 minus mu over r. When epsilon is negative, the orbit is bound. When epsilon is 0 or positive, the spacecraft escapes entirely. A Hohmann transfer orbit is the minimum energy path between 2 circular orbits. It is a single ellipse. Perihelion at Earth's orbit, aphelion at Mars's orbit. 2 impulsive burns are required. The first burn at Earth accelerates from the circular velocity of 29,785 meters per second up to 32,729. A delta versus of 2,944 meters per second. The second burn at Mars costs another 2,650 meters per second. The semi-major axis of the transfer ellipse is 1.262 astronomical units. Kepler's third law, T equals 2 pi times the square root of a cubed over mu, gives the transfer time. Substituting, we get approximately 298 days. That is exactly how long Mangalyaan took to reach Mars. The Oberth effect is perhaps the most counterintuitive insight in rocketry. It states that a rocket burn at high velocity produces far more useful energy than the same burn at low velocity. The proof comes directly from the work energy theorem. When a burn adds delta versus to a spacecraft already moving at V, the kinetic energy gain is m times versus times delta V, plus a small second-order term. The dominant term scales linearly with V. Double the speed at the burn point and you double the energy gain, for exactly the same propellant cost. Since orbital velocity is highest at Perigee, the closest point to Earth, all efficient burns must happen there. ISRO placed every apogee-raising burn at Perigee, where Mangalyaan was moving fastest, that is pure Oberth optimization. PSLV-C-25 placed Mangalyaan into a 250 by 23,550 km elliptical parking orbit. The spacecraft's total launch mass was 1,337 kilograms. 852 kilograms of propellant and 485 kilograms dry mass. The onboard liquid Apogee motor produced 440 newtons of thrust at a specific impulse of 308 seconds. Tsiolkovsky's rocket equation tells us the total delta V available. Delta V equals ISP times G0 times the natural log of the mass ratio. With ISP of 308 seconds and a mass ratio of 2.757. The total propellant budget is approximately 3061 meters per second. Every single design decision in this mission was driven by that number. The budget is split. Approximately 1094 meters per second for the 6 apogee-raising maneuvers. 648 for trans-mass injection. Just 5 for trajectory corrections. 1099 for mass orbit insertion. And 215 held in reserve. There is no waste anywhere. Between the 7th and 30th of November 2013, ISRO commanded 6 apogee-raising maneuvers. Every single burn at Perigee. After EAM-1, the apogee reached 28,825 kilometers. EAM-2 suffered a partial thruster anomaly and required a corrective burn. By EAM-4, the apogee was at 118,000 kilometers. EAM-5 pushed it to 192,000. Nearly half the Earth-Moon distance. The 6th maneuver on the 30th of November reached 600,000 kilometers. Approaching Earth's sphere of influence. Then on December 1st, the trans-mass injection burn fired for 1,328 seconds. Adding 648 meters per second. And Mangalyaan escaped Earth. For the spacecraft to arrive at Mars's orbital distance at exactly the moment Mars is there. Mars must be 23.6 degrees ahead of Earth at the moment of launch. This geometry repeats every 779 days. Roughly 26 months. Missing the November 2013 window meant waiting until January 2016. The trajectory design uses the patched conic approximation, dividing the journey into 3 separate two-body arcs. First, a hyperbolic escape from Earth's sphere of influence. Second, a heliocentric ellipse for the 298-day cruise. Third, a hyperbolic approach within Mars's sphere of influence. 3 trajectory correction maneuvers during cruise kept the spacecraft on track, costing just 5 meters per second total. Mangalyaan entered Mars's sphere of influence on the 21st of September 2014. 3 days before orbit insertion. In Mars's reference frame, the spacecraft is not in orbit. It is on a hyperbola, with more than enough energy to escape Mars entirely. The hyperbolic excess velocity V infinity is approximately 2,900 meters per second. As the spacecraft falls toward Mars, it accelerates. At periapsis, 365 kilometers above the surface. Vis-Viva gives us the speed. The square root of V infinity squared plus the escape velocity squared. Approximately 5,586 meters per second. The required capture orbit speed at that altitude is 4,672 meters per second. Therefore, the MUA burn must reduce velocity by approximately 914 meters per second. This is the most critical moment of the entire mission. On the 24th of September 2014, at 7:17 in the morning Indian Standard Time, Mangalyaan fired its liquid apogee motor for 1,388 seconds, consuming 249 kilograms of propellant, and decelerated by 1,099 meters per second. The burn occurred while Mangalyaan was behind Mars, in complete radio blackout from Earth, with a 22-minute one-way signal travel time. Real-time intervention was physically impossible. Every command was preloaded. The spacecraft executed the entire sequence autonomously. When the signal finally arrived at ISRO's ground station, it confirmed successful capture into a 365 by 80,000 km elliptical orbit, inclined at 150 degrees, with a period of 72.7 hours. India had reached Mars, on the first attempt, at a fraction of the cost of any previous Mars mission. The total delta V used was approximately 2,350 meters per second against a budget of 3,061. This is what orbital mechanics, the Oberth effect, and precise engineering can achieve when they work together. Mangalyaan operated for over 8 years before contact was lost in October 2022.